All right, so looking at the symmetric form of derivative, this is, remember when we did the alternate form, wasn't it nothing more than me just relabeling my points with different names, but doing exactly the same thing? Well, this one is actually a little different. What we're going to do, draw yourself a function over here just to talk about. So let's just do a generic kind of f of x here. Now, we're interested in finding the slope of the tangent line at a point, and we'll give the point a name. We're going to be specific. We're going to be at x equal to c. What are the coordinates of this point at which I want to find the slope of the tangent line? C f of c. Okay. So I'm going to draw my tangent line in. Red. So I have this nice tangent line at x equal to c, and I want to find its slope. Now, what we had done before is we had moved over a little bit in this direction and picked a point. And if I was doing the alternate form, what did I call this point? The alternate form. Not the first limit definition, the alternate form. X and f of x, right? And then if I was doing it in the original limit definition form, I would have said I moved over a distance of h, and I would have called my x-coordinates c plus h, okay? Well, this is kind of a mix of the original one and with a little new kind of caveat added in. I am going to call this c plus h, okay? This point would have the coordinates c plus h and f of c plus h. But then I decide that I don't really want to do the limit like we did originally, which is I let this point get closer and closer and closer, which meant that the h was going to 0. And technically, because it was a limit, could this point have been over on this side as well? Because you're doing a limit, you really have to look at it from the left and from the right. Now, if I look at those secant lines and draw them in, are they very good estimates of the tangent line at the beginning here? Like if I draw in this one little secant line to this point where I'm at, is that a good estimate of the tangent line slope? Not really. It only gets better as h goes to 0. So this method, take that off now, instead of looking at the limit on the left and the right and letting h go to 0, now what I'm going to do is I'm going to add another point. I'm going to add a point down here, and it's going to be equidistant going this way, and it's going to be at c minus h. You see where symmetry is coming in? This is why it's called the symmetric form. I move the same distance to the left and to the right of my point. What are the coordinates of this point? C minus h, f of c minus h. Now I'm going to draw the secant line in through those 2 points. And how good of an estimate is that secant line to the slope of the tangent line? It's pretty darn good, right? And so the idea with the symmetric form is instead of doing a limit and being off, 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 and not really getting good to you're really, really close, that if I could pick a point just a little bit farther away from it on either side and do a secant line between that, I'd get a really good estimate of what the tangent line slope is. Okay? And this is actually how you're counting. And then where did this formula come from? What's the top right here? F of c plus h minus f of c minus h. Yeah, here's y2 and here's my y1 that I'm using now. And then on the bottom, okay, here's my x2, here's my x1. What happens when you subtract those? You had c plus h minus c minus h, and that's exactly your 2h. Okay? So we're like, hey, this is a great method, right? And this is actually how your calculator is going to calculate derivatives for you. It's going to actually take whatever point you're interested in on the function, and it's going to move, and I'm not really sure what its actual h is going to be in the calculator. I have to look it up and see what it is. Maybe it's 0.1, 0.01. It picks a point, 0.01 on this side, 0.01 on the other side, and then just calculates the slope and says, hey, that's going to be my tangent line slope. Okay? And we're like, yeah, that seems great. That's a really good way to do it. Now here's the problem. Let's look at example 14. What can you tell me about, because we've just done a lot of work with this, the derivative at x equal to 0 on an absolute value graph? It does not exist. Okay, so we're going to come in here, here, and here, and we already know f prime of 0 does not exist. Now let me ask you, what do you think is going to happen if I were to actually do this using the symmetric form of the definition, which is pick a point, move over a little bit, pick a point. Yeah, what's going to happen no matter what I make my distance that I move away on either side, it will always have a secant line slope of 0. Oh, why didn't this method work on this one? What's wrong at x equal to 0? There is well, it is continuous. There is a cusp there, which we know does not have the derivative because the slope on the left and the slope on the right, you're not going to get the same value if you do the alternate form of the definition. So this is kind of what we call a failure of the calculator and using it. But we want to talk about the calculator because on the AP, you're going to have calculator multiple choice and calculator free response questions, where they're going to ask you to find a derivative. As long as you have a function kind of like what I have up here, which is smooth, continuous, has no cusp, and no, what's the other thing? Vertical, unusual, steepness, it's going to cause you to have a vertical asymptote. If you don't have any of that, then you're basically just going to use your calculator to calculate a derivative. You're not going to waste, now here's the mistake that I see a lot of students making on the AP. You're so used to algebraically showing us stuff that you'll start trying to find a derivative by doing it the long way and the algebraic way. But remember, what's the constraint you have on the AP? Time, and you want to be as fast as possible. So you have to resist. Even if it looks like a derivative that you can do by hand, pencil and paper, pushing it on the don't do it. If it's in the calculator section, you're going to pick up your calculator and you're just going to type it in and get an answer and move on and do the rest of the problems. Now here's how you do it on your calculator. Take the calculators out. All right, now my calculator has pretty print or math print on it. If your calculator does not have pretty print, then you can go to Texas Instruments website and read through the instructions and upgrade your operating system, and it will make you have an option of having pretty print, okay? I'm going to show you this first. I'm going to change, see how in my mode here I have math print and classic? Most of your calculators probably have classic. I'm going to put myself in classic to start with, and then I'll come back and show you what math print looks like. Math print's actually really, really nice because you don't have to remember anything about what you're typing in. It's in a nice form and it's easy. But we'll do classic first. All right, so let's suppose we want to do, the example was derivative of the absolute value function. Okay, and we want to do the derivative at x equal to 0. Under this math menu, right here, click on math. Do you see number 8 down here? You have a choice called in derive. It's going to find a derivative for me. It will not find a derivative function for you, but it will find an actual slope for a specific x value for us. How is it going to find it? It's going to use that symmetric form. It basically takes whatever function you tell it. It says, okay, I want to pick a point to the left and the right, and then I'm just going to calculate the slope, and that will be the estimate of the derivative. Is it going to be an exact answer? Because estimation on your calculator is not exact. However, for the calculator section, they don't want exact. They want you to just get an answer and then be able to use it. So what's the first thing you do in this, the format, if you have the not pretty print, math print, is I first have to say, well, what function? This one was the absolute value. Do y'all know where absolute value is? Under the math menu, move over to number, and choose number 1. So I need the absolute value of x, and then I'm going to put a comma. I'm like, okay, I've got the function in. All right, hold your thought. You have nice math print. We'll come back to you. This is more for the people who don't have math print. All right, so I have the absolute value of x. Then I need to put in there what am I taking the derivative with respect to here? What's my input variable? X. So I have to tell it, hey, I want to take the derivative of this function with respect to x. And then I put a comma, and I go, well, where did I want to find the derivative? At x equal to? What were we doing in the example? 0. So I put in my 0. All right, and so I'm actually showing you this for the first example with one that's going to give you the wrong answer. Because it's going to tell me 0. Because it's using the symmetric form of the definition and picking a point on either side, and that's a failure. So the first kind of moral about using your calculator is if there's a cusp or unusual steepness or a discontinuity, even if there's a discontinuity, you can't use this. Because even if there's a discontinuity at x equal to c, if I move to the left and I move to the right and pick a point, there are going to be points left and right. So it will actually calculate a derivative when you do not have a derivative. So I want you to be careful about it. However, if I know there's no cusp, and I know that there is no unusual steepness, it will find a derivative just fine for me. Let's do the one that we just did in the one example. Let's go to nDerive. I'm just going to do second entry because I don't want to type it in again. Let's do x squared. So let's delete that function and insert a square. So my function is going to be x squared. And we were doing it at x equal to 1. What was my derivative at x equal to 1 for x squared? 2. Right? So we put that in. Oh, 2. There you go. Are you going to have simple functions like this in the calculator section? No. You're going to have really complicated, long functions with square. I mean, that's why they're doing it in the calculator section. You don't have to find those derivatives by hand. You're just simply going to plug them into your calculator and calculate them. Okay? Well, hold that thought. All right, now let's go. Let me show you what pretty print looks like. Okay, so I'm going to change my mode into the math print and go back to my home screen. All right, so now that I'm in math print, I'm going to do the same thing. I'm going to go math. I'm going to choose the nDerive number 8. And now look at what it looks like. Now, do you see why I showed you that new notation, the derivative of the function with respect to x? And there's one new thing that we're adding in. This little line really just means evaluated at some x equal to a number there. So what's going to happen here is we're going to say, all right, what are we taking the derivative with respect to? X. So I put that in. And then I go, what do you think should go in this spot? X squared. The function, what function am I taking the derivative of? So we put in our x squared. And notice that once I added the x in, what happened over here is it's saying, hey, now it's x equal to. Because now you're saying, well, what x do I want to take the derivative at? What were we doing? 1. So you put in your 1. And so this notation is saying, find the derivative, the slope of the tangent line on x squared with respect to x at x equal to 1 and tell me what it is, and it'll tell you 2. Say, I like math print because it seems to make more sense to me. I don't have to remember what syntax I have to do, function, variable, value. Here you just fill in the spots wherever you fill it in. So if you want to upgrade your calculator, do that. All right, so now this really only tells you one slope though, right? What if I wanted to see what the picture of the derivative looks like? Have it for all, like, you know, try to get an idea of a general formula. All right, let's go to y equals. All right, now a couple things I'm going to show you here. What I want to do is I want to put x squared, the function that I'm interested in y1. Now, and again, I'm simplifying here. Obviously, if this was on the calculator portion of a multiple choice or something, you're going to have something way more complicated than just x squared. Okay? So when I start to type in my derivative, I am still going to go to the math menu and get my nDerive 8. I'm taking it with respect to x. Instead of me retyping the function right here, because yeah, x squared is simple and I could do it very quickly, but that's not the point. You're going to have something, you know, really long and complicated. I don't want to make a mistake and miss a question for data entry error in my calculator. I've already typed it in once. Where can I go get something that's going to help me not have to type it in again? Yeah, go to the vars menu right here, which is right here above the, next to the clear. If I go to vars, what kind of a variable am I looking for? A y variable, so you move over. Choose a function, because y1 was the function that I'm interested in, and I choose y1. So you, in general, a lot of times when we're doing this type of thing, notice I can actually just leave this in my calculator when I'm on the AP and just change my y1 to be whatever function I'm interested in. I don't have to keep retyping this in every single time. It's there, and it will always refer back to y1. But now, I don't want to do just one slope. What do I want to do here? What do you think I should put here to get a general formula? Instead of putting x equal to 1, put x equal to x. Let's just say do it for all of them. So we're just going to put this in as x and say, hey, you go ahead and look at the calculator. Let's calculate it for all of them. Now when we go to our graph, let's just do zoom 6. Now depending on your battery strength, it might take a little while to calculate this, because what it's doing is calculating all of your derivatives at different points, and then it'll start plotting them. And eventually it'll start coming in and plotting it. Does it make sense that that's the function that I got? What was our derivative of x squared? What was our general formula? 2x. Oh, right here, isn't that 2x? If I go over 1 and up 2, that is y equal to 2x. Now, let's make some connections between the function and the equation of the derivative, which is the slope of the tangent line at any point. Let me go to this. All right. What do you know is happening? And this is, we're going to go back to a homework question that we had in that worksheet 4.1, where you were sketching the derivatives. What's happening on the function here, on this piece of the x squared? It's decreasing. What can you tell me about the slopes on a decreasing section of the graph? They are all negative. So you're like, oh look, down here, the derivative is negative. The function was decreasing. So when f is decreasing, your derivative f prime is always negative. Okay, so that's fact number 1. All right, fact number 2, what can you tell me about this vertex right here? What can you tell me about its slope? It's 0. It has a horizontal slope. So every time you have a vertex, okay, vertex on f, a nice vertex like this little smooth curve. Okay, obviously I'm not talking about cusp here yet. So this is vertex on f, then what's going to be happening on the derivative? What's that going to be equal to? It's going to be equal to 0, which means it's going to have an x-intercept. Right? And then as we go along over here on this side, what's the function doing over on this side? Increasing, so f is increasing. What does that tell me about the derivative? The derivative is positive. And so those are the kinds of things that you're going to start looking at in order to tell, how do I sketch the picture of a derivative? I'm using these basic facts. Okay. The other thing that I'm going to use, and we'll learn once we start doing the shortcuts for the derivatives, the derivative, if you're doing power functions, the derivative of a quadratic is always linear. The derivative of a cubic is always a quadratic. The derivative of a fourth power is always a cubic, and so on and so on and so on. So I'm going to use a little bit of that as well looking at it. All right, so what I want to do right now is, let's go back to the notes here. Let's see, was there another example in there? Oh, can you summarize here about your calculator? Like, when can you use your calculator? When do you have to be careful about your calculator? So go ahead and summarize that here in example 14 for me. You check what you put up on yours with what I have for mine. So using the calculator, we got the derivative was 0, but that's not correct, because we already know that it should be, does not exist. And really what I want you to get out of this is the symmetric definition is great, but it fails when it's not continuous. It fails when it's continuous and it has a cusp or unusual steepness. So you want to be very, very careful about that kind of a derivative. Just one last thing to kind of show you why unusual steepness is not going to work. let's take a look at, what was a nice function we just did in the previous page that had unusual steepness at x equal to 0? Cube root of x. Do y'all know how to put the cube root of x into your calculator? You can do the x root, but you can also just go, a cube root is a power of 1/3. So I'm just going to type in 1 divided by 3 as my exponent. If you are not in math print, you see how in my math print that I have my 1/3 here already up in the exponent? If you have to do caret 1/3, you have to put parentheses around the whole 1/3 so it knows the whole 1 divided by 3 is the exponent. So be careful about that. I'm just going to go to the home screen and I'm going to do my derivative, number 8. Oh, look at the home screen. I can actually, I put it in y1, and you're going to be like, oh, why did she put it in y1? Because even if I'm on the home screen, I can do vars, y vars, function y1, instead of typing it in again. And I want to find the derivative at x equal to 0. What do we know about the derivative at x equal to 0 for this function? It does not exist because it had a vertical tangent line that had undefined slope, unusual steepness. What's the calculator tell me? 100. Why is the calculator telling me 100? Because it picked a point a little bit to this side and a little bit to this side, and the 2 points that it picked, the secant line, is the secant line vertical? No, it's almost vertical. It's getting more vertical, but it's not really vertical, so it's going to be like just fine. It's going to calculate a slope, but it's not going to be what you're looking for, and so that's, you have to be careful about that. Okay? All right, let's take a look in our notes then, now that we've had this discussion. PDF. Speak out. Where we were sketching the derivatives. Okay, and when I walked around, I did take a look at your papers, and some of you really need to revisit on this little section. All right, so let's look at the behavior of f. I'm going to help you out on this one right here. The first thing that I'm going to do is I'm going to kind of just put some characteristics down below here. What's the function doing from negative infinity to about this negative 3? All right, so f is increasing. What does that tell me about the derivative? F prime must be positive. Okay? From my negative 3 all the way up to 3, what's f doing? Decreasing. So my derivative, f prime, is negative. And then from 3 on, my f is increasing again, so we can know that our derivative is positive. Okay, so we get that. What's happening here at negative 3 on the original function? What do you have? On the original function, you have an slope of 0 because we have a max. So we know that the f prime has to equal 0, which is an x-intercept. And then at 3, we have a min on the original, but that would make my derivative still. What's my derivative there? What's the slope of the tangent line? Is it still 0? Yeah. Doesn't matter whether you're a max or a min, you're still going to have a nice slope of 0 there when I have a smooth vertex. So that would be an x-intercept. So when I actually start sketching the derivative in here, I go, all right, well, at negative 3, there should be an x-intercept. At 3, there should be an x-intercept. All right, now let's think about the slopes in between negative 3 and 3. Well, actually, let's just go all the way over here. If I'm looking at the slopes over here, what kind of a slope is it right here for the tangent line compared to here? The slope itself is becoming, what's it approaching as I move up? The slopes are approaching 0. But so they're positive and approaching 0, which means they must be decreasing. All right, so I'm going to add that in. F prime is decreasing here. Now let's talk about in between here. What do we know about these slopes on this side? I'm having trouble sketching close enough to the thing. Are they positive or negative? They're negative. Now what happens in here? It's becoming more steep for a little while, but then what has to happen? It has to become less steep. Where's it switching from being more steep to less steep? At a, what would you call this point right here? Point of inflection, okay? And let me not put that in blue, because that will confuse us later. All right, so right at this point of inflection would be kind of where we have the most steep negative. Now, let's think about this. If I am negative and becoming steeper, like maybe I have a slope of negative 10, the next one would be a slope of negative 50. Is that decreasing or increasing? Think of a number line. If I have a slope of negative 10 and then I have a slope of negative 50, that means I'm headed in that direction. Am I decreasing or increasing? I'm decreasing. So for the beginning part, f prime should be decreasing. Then it hits that point of inflection, and then it becomes less steep, heading back to 0. So f prime would be increase. Oh, what has to happen right at this point of inflection on the derivative? It has to be a vertex. Okay, so now we know f prime has a vertex. And then over on this side, I'm 0, and now I'm positive again, and I'm getting steeper, so f prime is increasing. So we look at all of those things, and now we say, can we sketch it? Do I know what the vertex is? Well, can we estimate what this slope is by drawing the line in? Yeah, let's say we went down 1 over 1. So let's say it's negative 1 there. So the slope at 0 is negative 1, so I'll add that in. So I estimate. And then I start putting in the picture. And that would be the picture of my derivative. Everybody see kind of how I'm revisiting that? Yeah.
In physics, it looks a lot different.
In physics, it looks like, no.
Well, like when we do in physics, like the derivative graphs, he makes like really, really sharp corners and like flat lines for this.
Well, it depends on what's happening. On this, I'm also using the idea that this is probably a cubic.
Oh, okay.
Okay? And so I know the derivative of a cubic has to be a quadratic of some sort, so I'm doing this.
Okay.
However, if I'm doing a quadratic, the derivative of that would be a linear. All right, so I want you to go back and revisit this based on this discussion. You have textbook homework tonight, okay? And then we'll kind of try to wrap up 3.1.